or f double prime is undefined. And then second, we want to use these x values to determine the test intervals, similar to what we've done in the past. And then last, we're going to test the sign of f double prime in each of these test intervals. Okay, so let's take a look at an example. So with example 1, we're just exploring the concavity of these functions. In part A, we're looking at the graph of f of x squared. Now, f of x squared is going to be concave up over the entire real line because the second derivative, if you take f double prime of this, you get 2. And this is going to be positive for all of your x. So notice that your f double prime is positive for all of your x, so it's always going to be concave up in this case. In part B, we're looking at the graph of f of x equal to the square root of x. Now, this is going to be concave down for all of your positive x because the second derivative is going to be given by this. And let me see. This is going to be negative for all of your x positive. So again, this f double prime so again, in example 1, part B, we were given f of x equal to the square root of x. And again, this is going to be equal to x to the 1/2. So then your f prime is going to be 1/2 x to the minus half. So then your f double prime is going to be a minus quarter x to the minus 3/2. That's where this comes from. Now this, if you write it without a negative exponent, is the same as a negative 1 divided by 4 times the square root of x cubed. Okay, since the 2 is in the denominator, it tells you it's the square root. And so for any positive x you choose in here, so as long as x is positive, this denominator is going to be positive, the numerator is going to be negative. So for your domain, which is positive x, this function is going to remain negative. So that tells you, again, since the graph of this, or the graph of this is going to be concave down because the second derivative is going to be negative for all of your positive x. So here your second derivative is negative here. So that's why it's concave down. Or in other words, it's curving, the curve is opening up downward. Okay. Okay, so with this example 2, it says, okay, so with example 2, it says determine the open intervals in which the graph of the function is concave upward or concave downward. Okay, so we're given this function and we want to find the intervals in which the graph is concave up or concave down. So what we're going to do is work it the same way that we did when we were discussing the increasing and decreasing functions. So again, this is example 2. Again, determine the open intervals in which the graph of the function is either concave up or concave down. So if we're given this f of x equal x squared plus 3, like this, 6 divided by x squared plus 3. Let's see. So again, here we have our guidelines for applying the concavity test. Here, again, we say when testing for concavity, if your f double prime is positive, then it's going to be concave up, and if f double prime is negative, it's going to be concave down. So again, for our guidelines, we say locate your x values which your f double prime is 0 or undefined. So it's similar to our critical numbers in the previous discussion. So then use these values to determine our test interval, and then test the sign of these. So first we need to find f double prime. So if this is our f of x, I'm going to rewrite the original function. So I have f of x equal to x squared, or 6 divided by x squared plus 3. I'm going to rewrite this as 6 times x squared plus 3 to the minus 1. So now when I find f prime, I can just use the chain rule. So then my f prime of x, the exponent falls, so I have a negative 6 times the inside. Subtract 1 from the numerator, becomes a minus 2. And then times the derivative of the inside, which is going to be 2x. I'm going to simplify this down a little bit. So then this is going to become a negative 12x, and I'll leave it like this, x squared plus 3 to the minus 2. So now from here, if I want to take this derivative, I could either use the product rule with the chain rule, or I can write it as a fraction and use the quotient rule. I'm more of a fan of the product with the chain, so that's what I'll do. So for my f double prime, so now if I'm using the product rule, it's going to be this first times the derivative of the second. So it's going to be this minus 12 times the derivative, or in other words, my d by dx of this x squared plus 3 to the minus 2. So I got to take this derivative. So the first times the derivative of the second plus the second times the derivative of the first. So my d by dx of this negative 12x. Okay, so then this is going to be equal to a negative 12x. This derivative is going to be, alright, so it's going to be times a negative 2. So this is going to be x squared plus 3 to the negative 3 times the derivative of the inside, which is another 2x. Okay, so I had to do the chain rule there. This negative 2 fell in front, subtract the 1 from the exponent, and then I have times the derivative of the inside, which is just going to be 2x. Okay. So then it's plus x squared plus 3 to the minus 2. Now this derivative here is just going to be negative 12. So times a negative 12. Okay. So let me just try to clean this up a little bit. So this is, now let's see, I have this 3 that goes down. In my numerator, I have the 12, the 2, and the 2. That's 48. So it's going to be a positive 48x divided by, I have this x squared plus 3 cubed. I have 2, 12, and 2. 24, 48.